Thank you, Attila. Thank you very much for the invitation and for the introduction. So my name is Igor Girault. I'm a French PhD student. I'm currently in my fourth and hopefully last year of PhD in the University of Rouen in France, under the supervision of Dr. Dominique Todisco from the same university, Professor Damas Mouralis, and the supervision of Professor Fabiana Martin from the University of Magallanes in Chile. So I will talk today about the one aspect of my work as PhD student, which is the chronology and the deglaciation style of the Patagonian ice sheet, and the chronology of the regression of an ice dam lake in a site very important for archaeologists in Patagonia, which is Cerro Benitez, that I will present you. It's an island with it's a small hill with caves, with a very rich and important archaeological and paleontological record of the late Pleistocene of southern Patagonia. So this work has been submitted as an article in collaboration with Attila Siner, Mehmet Akif Sarıkaya, and Cengiz Yildirim. So I apologize for the pronunciation because my Turkish is not as good as the French of Professor Siner. And this will be part of my PhD that focuses on the geoarchaeology of the cave of Cerro Benitez. So how did the caves form, and when did they become accessible to the human peopling and megafauna? So here I show you our sources of funds. So we are funded by several international projects, Chilean, French, and also by for this aspect of the work by the Istanbul Technical University, and several grants that I awarded as a PhD student. So I will introduce you first to our location of study, Cerro Benitez, and I will try to show you why it is interesting for us, for both archaeologists and geomorphologists. So Cerro Benitez is, as I said, a small hill that culminates near 550 meters above sea level. It's located at the southernmost tip of the American continent, which is a peninsula called Patagonia. We are near 51 degrees south, so it's the same range of latitude as England, for example. And this small hill hosts several caves and rock shelters that delivered Pleistocene megafauna from near 18,000 years before present, and also one of the oldest unequivocal archaeological record of Patagonia, dated from near 13.5 thousand years before present. So this site is very important because it's the first to be colonized by human at this latitude. Hence, it's probably the last continental territory to be colonized by human by the late Pleistocene. So here you can see a few examples of archaeological material that is found in the caves, earth, so made of charcoals, and here lithic material, lithic tools made by man and dated, as I said, 13,000 years before present. The caves are also very well known for the megafaunal material, as I said, with the oldest megafaunal bones dated around 18,000 years before present. Here you can see one of the caves. It's the biggest, the Milodon cave, that also gave its name to the Milodon Cave Natural Monuments, which is a protected area in which we have to work if we want to go there. And here an example of soft tissues, very well preserved, of megafauna. Here a ground sloth of this animal that you can see in the corner. The Milodon, it's an extinct ground sloth that was one of the biggest, if not the biggest, representative of the Patagonian late Pleistocene megafauna. So there is Milodon, ground sloth, there is other species of megafauna, and all became extinct shortly after the arrival of man in the area. So for this reason, those caves have a great importance to reconstruct the processes of colonization of the area by man, and then the subsequent extinction of the megafauna. So one of the important aspects of the research in this area is to reconstruct the environmental changes that immediately preceded the arrival of megafauna and man. It is especially important because we are located at the vicinity of a former ice sheet, the Patagonian ice sheet. So nowadays, Patagonia is, as I said, a narrow peninsula, and the subduction of the Antarctic plate produce a mountain range, 1,600 kilometers long, the Patagonian ends. So it's the tip, the southern tip of the Andean mountains. And because this mountain range intercept at these latitudes, at the southern mid-latitudes, the westerly wind, then it produces a rain shadow effect that create a very, very strong gradient of precipitation and a very strong contrast of precipitation between the west coast and the east coast. So the west coast is very wet because the mountains intercept the winds, and then at these latitudes and at this elevation range, this promotes the accumulation of snow and then of glaciers. So nowadays, you can see here in gray the current ice fields of the area. It's the three largest ice fields of the southern hemisphere out of Antarctica. And here in white, you can see the former extent of the Patagonian ice sheet that totally covered the area during the last glaciation. So it was a continuous elongate ice sheet, one of the biggest on Earth, besides the landscape of the northern hemisphere and Antarctica. So it reached at its maximum around 500,000 kilometers square and supplied 52 main outlets eastward flowing ice slopes that were flowing from the Andean range towards the Atlantic. So here an example of the beautiful landscapes inherited from the glacial history of the Patagonia. It's the Strait of Magellan that cut the southern tip of South America. It's actually a glacial valley incised by a very, very long and wide ice slopes. And here at the bottom of the screen, you can see one example of a drumlin field in the area of the Strait of Magellan, produced at the bottom of this former ice slope. But we are working a little bit more in the north, almost 300 kilometers northward, in the area of the former Ultima Esperanza ice slope. So in this region, the glaciers eroded an intricate network of fjords connected to the Pacific Ocean that were first explored in the 16th century. And these fjords now border the current the modern southern Patagonian ice field. So you can see here the modern glaciers are almost or near calving in the fjord, in the sea. So here I will show you a more detailed geomorphological map of the Ultima Esperanza fjord. So this is this narrow inlet that connects to the west to the Pacific Ocean. This is a geomorphological map that was realized both from remote sensing data mapping and a compilation of previous works that I will summarize quickly hereafter. So we have to imagine that back to the last glaciation, there was several glaciers coming from the fjords and merging into a very wide ice slope that deposited several moraines, several marine complexes, while flowing eastward. So the most external complex was dated 45.7 thousand years by terrestrial cosmogenic nuclide dating. Then there is a second glacial advance that deposited more internal moraine complex, so near 10,000 years after. You can see here one of the moraines obstructing the glacial valley. And then we have other more internal moraines that have not been dated yet until now. For example, this moraine that you can see here, very close to the fjord. So we have at least, during the late Pleistocene, 3 main glacial advances. So every time more that deposit moraines at more internal position. And the biggest known advances date back from the marine isotopic stage number 3. So as I said, around between 30 and 50,000 years. After the glaciers retired, after the glacier retreated, you can see here on this thin blue line, it's the paleo shoreline. So we know that a very wild proglacial ice dam lake developed in the former glacier bed, and the lake was dammed to the west, to the east, by the moraine complexes, with an outlet here at 135 meters above sea level, and was dammed to the west by the retreating glaciers. But until now, we didn't know how long did this proglacial lake exist. And this is important because, as you can see on the map, this proglacial lake was located all around Cerro Benitez. So this hill with its caves was actually an island surrounded by a proglacial lake. So it's important to know what was the lake level, to know if the caves were located under or above the lake level, and more important, the chronology of the lake regression, to know when the caves became open for megafaunal and then later human colonization. So that's the questions that will guide the rest of our work there. So first, when did Cerro Benitez accessible to megafauna and the early human peopling? And it means when first did the Patagonian ice sheet retreat from the area, and then when did the lake regress from Cerro Benitez? So to solve these problems, we use first geomorphological mapping on GIS in order to map the former glacial and deglacial environments. So to this aim, we use both remote sensing data mapping from satellite images and digital surface model building, and of course, field mapping. So field mapping was based on mostly pedestrian prospection that consists in working in the area and map all the landforms, map and identify all the landform that we can see. We also use as a support aerial drone photography, as you can see here, in order to map landforms on a wider area. And also in the field features analysis in order to characterize better the environment of deposition of the sediments that we find on the area. So here you can see one of the 8 sedimentary outcrops that we studied on the field, and on which we based our paleoenvironmental reconstruction. And second, then we will see later, in order to better constrain chronologically the reconstruction of the paleoenvironmental changes, we use terrestrial cosmogenic nuclide surface exposure dating that I will detail soon. So this is the result of the field species analysis. So after analyzing a lot of outcrops, I produced a synthetic table that summarized the characteristics of the deposits, and hence, in this column, the reconstructed depositional environments. So this is the basis to map to define the superficial deposits, and then to reconstruct the extent of the former environments. So then we produce this geomorphological map of Cerro Benitez. So you can see here, there is the hill, in the north, a glacial valley with several deposits. In the south, the valley that connects to the fjord, several kilometers more in the south. So I will show you some examples, that will show you first the landscape and what kind of landforms we mapped there. So the highest landforms were roches moutonnées, so reliefs created by a glacial abrasion at the subglacial bed. So that means if we find this at this elevation, it means that the summit was covered by the ice lobe. Then at lower altitude, we find another kind of subglacial erosional landform. This is knee channels. It's channels incised by subglacial meltwater. So here again, the orientation of the channels give us very, very useful information about the nature of the meltwater erosional processes, but I will not go too much into the details about that. Then, after the subglacial landforms, we find ice marginal landforms that you can see here. For example, lateral moraine that is later cut by the lacustrine erosional platform. And we also find a delta at the eastern extremity of Cerro Benitez that deposited between 2 converging ice margins and was later truncated as the lake regressed. Here you can have a better look of the erosional platform. So as I said, we know that there was a lake at this altitude, and besides the delta, the lake is marked by paleoshorelines that consist in lines of notches cut partly by the waves and more probably also by the frost weathering at the lake surface. Here again, I will not enter too much into the details of the processes inferred in the shaping of the lake shore. But the most important is to notice that we can see and reconstruct clearly with different paleoshorelines the successive lake levels. So we found 3 successive lake levels, the highest being 155 meters above sea level. Then we have another notch around 148, and then another lower at 140. So we have 3 successive paleoshorelines that mark the regression of the lake, and the highest being backed by the very high notches, almost cliffs, as you can see here. So here there is Cerro Benitez, and here the erosional platforms. And finally, at the lowest elevations, we find glacial lacustrine deposits that consist in very, very fine-grained deposits, clays, resulting from decantation in the lake, with embedded dropstones, so erratics that were conveyed by melting icebergs and then dropped at the bottom of the lake and sedimented. So with this map, we can already produce a relative chronological frame based on the shifts in the sedimentary dynamics that we identified. So first, we identified first glacial advance, during which the ice slope covers Cerro Benitez. Then a second, more restricted glacial advance, during which the ice slope deposited lateral moraines up to 220 meters above sea level, and then the summit of the Cerro Benitez was left at the nunatak. Then an early stage of deglaciation, a stage of ice downwasting. So during this stage, as the ice surface lowered, it accumulated sediments and at the ice margin. And then a second stage, a later stage of deglaciation, during which the ice margin retreated, and then the ice dam lake expanded to the west, then generating the onset of glacial lacustrine sedimentation and lakeshore erosion. So this is our chronological frame. Now we have to use it as a frame to interpret the exposure dates that we will produce, and hence to use the exposure ages of the erratics in order to constrain into an absolute chronology the relative chronology that we made. So here, I don't know if you all are familiar with the method of surface exposure dating that I will try to introduce very briefly. So it relies on the reaction in the high atmosphere triggered by the incidence of cosmic rays that produce particles from spallation. There is only very few of primary particles that reach the sea level, but there are more secondary particles produced by the cascade of spallation reaction in the atmosphere that reach eventually the surface of the Earth. And some of them have enough energy to generate spallation reaction and then produce new nuclide that we call then terrestrial cosmogenic nuclide, also called in situ cosmogenic nuclides. One of them is the beryllium-10. Why we target this nuclide? It's because the attenuation length, and this is the quantity of material that is necessary to attenuate the production rate of the nuclide. So his attenuation rate is around 160 grams per centimeter square. So that means that in quartz, it will be attenuated very fast under the surface of the erratic. So for example, in the quartz mineral. So that's why it's suitable for surface exposure dating, and also because it has a half-life of 1.4 million years. So it takes very long time until the production rate is compensated by the disintegration of the nuclides. So it's perfectly suitable to date the surface exposure in the chronological range of the last glaciation. So the sampling strategy that was led by Attila, Akif, and Cengiz was to use the erratics block as a dipstick to estimate the rate of ice thinning. So we started to sample back in December 2017 from the summit of Cerro Benitez, and then going down at different elevations in order to have a good cover, a good elevation range of surface exposure ages. So we sample actually more than 11 erratic blocks, but eventually 11 of the erratic blocks that were sampled yielded enough quartz to be analyzed further. The preparation was done here at the university, the Technical University of Istanbul, under the direction of Attila, Cengiz, and Mehmet, Akif. And later, the samples were sent to the Scottish University's Environmental Research Centre to be analyzed with an accelerator mass spectrometry. So there, the samples prepared by the team of Attila, Akif, and Cengiz in Istanbul were later analyzed, and the concentration of beryllium-10 was determined with spectrometry. Then, using specific beryllium-10 production rates and taking in account all the parameters that I will not detail here, we can calculate the surface exposure edges. And I will now present you directly the results of the edges that were calculated. So as you can see, we obtained two non-overlapping populations that present very distinct elevation ranges. So you have a first population, older, with a median around 34.5 thousand years. That's located at elevations above 220 meters above sea level. And then you have another population. It's the erratic blocks located on the erosional lacustrine platforms with a median near 70.8 thousand years. So you clearly have two distinct exposure phases. And from that, if you interpret those phases, so we can say that the upper erratic blocks were deposited by the ice because the lake never reached that altitude. And then the lower erratic blocks, since they were exposed at this moment, hence they give a minimal age of ice retreat from the second advance that we previously identified. So here, we reconstructed the extent of the ice lobe through the last glaciation with correlating our ages with previous ages yielded on the external moraines. So we can identify that the phase that covered Cerro Benitez, our area, is the same that deposited the marine complex that we saw earlier. So during MIST 3, and then by correlating the maximal possible altitude of the second advance to the inner moraines deposited by the ice slope, we can reconstruct, we can have an idea of the extent of the ice slope during its second advance. That happened then between the MIST 3 and the age of the erratics. So between MIST 3 and 21.3 thousand years. So that means that in our area, and that's actually very common in the southern hemisphere, the ice slope extent shrank to its half prior to the global last glacial maximum, that is 21,000 years. So now we will try to go further and try to interpret better the real meaning of the surface exposure ages. Because until now, we took only the maximum, we count the maximal and the minimal ages. But we will try to go further and make a hypothesis on the significance of the exposure age in a glacial lacustrine erosional platform. So in this kind of environments, erratic blocks can have several origins, several distinct origins. They can come from, they can be deposited by the glacier and deposited at the ice margin. Then, if they are overlain with glacial deposits, they need to be washed out by erosion, by lakeshore erosion, to be exposed. In the other hand, so if they are not washed out, they will not expose, and there is no date, there is no age. In the other hand, they also can deposit from iceberg melting. So it can be also ice rafted erratic blocks. But in all cases, we assume that they deposited under the lake level, so under 155 meters. In every case, because the lake was already present as the glacier retreated. And considering a mean attenuation rate in water around 1.6 meters, because the density of the water is less than the density of quartz. So if we calculate the corresponding column of water, we find around 1.6 meters. It means that the production of beryllium-10 starts when the column of water above the erratic block drops below 1.6 meters. Hence, in every case, the exposure event that we date with beryllium-10 is assumed to be the regression of the lake. Whether the erratic block deposited by the glacier or iceberg melting, or was it overlaid with glacial deposit or not. In every case, we can make the hypothesis that it dates eventually the lake regression. So hence, if we make this hypothesis, we can go further, and we have to suppose that actually the ages should be older for the uppermost erratics and then younger for the lowermost erratics. But that is not always the case in our result. But considering that we have very, very wide standard deviations, that could be an artifact, a statistical artifact. So we will try to recalculate the probability distribution of the ages by taking in account the hypothesis that actually the real relative chronology of the blocks is that the younger or above the older, sorry, or above the younger. So for that we use that we call Bayesian statistics, that consists in refining the probability distribution based on an arbitrary constraint. Here, the constraint that we will introduce in the calculation is the relative chronology model based on geomorphological evidence. So in our hypothesis, the highest erratic blocks are cannot be younger than the lower erratic blocks because it's exposed as the lake level falls. So for each age will be recalculated and bracketed by the exposure age immediately of erratic blocks located immediately above and under the edges. And in addition, we use to constrain the whole model radiocarbon data that have shorter standard deviation produced by an earlier study, but at very lower elevation. So each prior age is recalculated as posterior age. We used a software named Chronomodel. It's very recent and used mostly by archaeologists until now, but it presents interesting tools also for geomorphologic problematics. I will show you the results of the age modeling. So you can see that here in gray, the original ages are moved and deformed by the model in order to fit with the chronological, with the relative chronology that we asked the model to model. So we can see here, it doesn't change a lot because the ages are already very close to each other, but we remodel the highest erratics to 36.9 thousand years, and then the lowest erratics of the first deglaciation phase to 31.9 thousand years. So from that, we can assume and calculate a rate of ice thinning that represents a thinning of at least 300 meters in 500 years. So, and that happens during this 3 and will not be covered anymore by the ice after. So almost 10,000, almost 15,000, between 10 and 15,000 years before the last glacial maximum. And then now concerning the Deglaciation platform, we see that the model ages also fits well, except in one date where the age was moved to younger dates. But in general, it fits well with the original dates. There is no need to deform the existing dates. And that shows that the regression from 148 meters above sea level to 136 meters occurred between 21.7 and 16.9. So it thousand years. So it represents a regression rate of 2.5 millimeters per year. And considering the context and other calculation that I made that take in account the estimated volume of ice, we can say that it fits with the predicted post-glacial isostatic relative uplift. So the differential uplift between this part of the lake and the outlet. So hence, this regression, this early regression, could be due to the tilting of the glacial accretion basin that immediately followed the retreat of the ice margin. So as the ice margin retreats, the lake basin tilts and cause a forced regression at a constant outlet lake level. Hence, that also implies that megafauna colonized Cerro Benitez as an island, because our older dates are or around 18,000 years before present. And then after that, we have to move from this age at this altitude to this more recent age at very lower altitude, as indicated by the radiocarbon date. So that means that the regression, the local regression, hence increased at an increased velocity. So we can calculate a rate of near 40 millimeters each year. And since the lake level fall under the lake level at the outlet of the lake, it means that the drainage of the lake reversed, and the lake that was formerly drained to the Atlantic, as we saw in the first on the first slides, then reversed and drained to the south to the Pacific Ocean at until the total drainage of the lake. So I don't know if I still have a lot of time or no, but I would like to make some concluding remarks. So the points that are highlighted by this study, the most striking points is that first, we evidence that the demise of the ice slab occurred well before the global last glacial maximum. And then the glacial advance that occurred during the global last glacial maximum was reduced to its half. Then at a more local scale, we evidence that it's probably differential postglacial isostatic rebound that caused the cessation of the development of the lacustrine erosional platform, because it caused the local lake regression, and hence that caused the cessation of the cave development. And that happened prior to the drainage of the lake. We also evidence that Cerro Benitez was probably, according to our Bayesian age model, colonized as an island. So this can have implications in terms of paleoecology and reconstruction of the processes of megafaunal dispersal to the formerly englaciated areas. And there is also a more methodological implication, because using Bayesian statistics in this context, it's still a little bit new. It's not, it has not been done very often, especially in Patagonia, to reconstruct lake regression chronological models, especially with exposure ages instead of radiocarbon dates. But we see that if the model is constrained prior to its building by a very strong and reliable geomorphological interpretation of the exposure edges, so here our relative chronological models, it gives results that fits very well with our interpretation and our knowledge of the dynamics, the glacial dynamics and post-glacial dynamics of the area. So if it is well constrained, we can use exposure ages to go a little bit further than the real ages and to remodel it in order to have a more precise chronological absolute model. So I will stop here for the presentation. Thank you very much, and thank you very much to all the people that made the fieldwork possible, and especially to Professors Attila, Cengiz, and Akif, that did a lot of work to sample in Patagonia to help us in determining the sampling strategy, and then to prepare the samples and calculate and interpret the edges. So this work will be published in collaboration with them, and that's why I'm very, very pleased I was very, very pleased to present it to you at the University of Istanbul.